In this section, we will build on the idea of area under the curve that we started in the last section, but using the definite integrals, which is a way to find the area under the curve. So if in the Riemann sum, which is what we did last time, using the left endpoints, right endpoints, midpoints, that's what the Riemann sum is, or a way to compute area under the curve. So if the number of rectangles n is approaching infinity, you can actually use it as a limit, then it can be shown that this area that we talked about last time using n rectangles, but we assume that they're going to infinity. So you're using as many as you can, basically. Remember, the more you use, the better the approximation is. Then we can also show that it is equal to the integral from a to b. So notice now we have, this is why it's called definite, it's defined on an interval of f of x dx. So now we are actually going to use integral to compute specifically the area, and we will get a number as the result. So the delta x is approaching 0, or delta x pretty much is going to become dx. Once again, that's why we have dx within the integral. And the area is approximated. So now we're going to use something called Fundamental Theorem of Calculus, which is that amazing theorem. I think I mentioned it before, where you can relate the area under the curve to something like the antiderivative, which are supposedly two different ideas to begin with, but they are related. So in 7.1, not too long ago in the beginning of this chapter, we defined indefinite integral, which was basically integral of f of x dx, which will get the antiderivative plus c, a constant. Or in fact, we're actually getting a family of functions, basically. So you get a function as a result, plus a constant. Now in this case, in this section, we're going to get a numerical answer, which is a little bit different, but the idea is very similar. So what we do when we compute a definite integral from a to b, so you see these endpoints, or limits of integration, sometimes that's what we call them. You compute the antiderivative as before, but then you're going to evaluate it. Notice how I put this little vertical line that a lot of textbooks use also, and it's from a to b. Okay, and then how you plug it in, you plug in the upper limit first, which is capital F of b, minus the lower limit, which is capital F of a, and we'll get a number as the result. Okay, so let's practice with that idea a little bit. So say we had an integral from -2 to 4 of -3 dp. So -3 is your function and p is your variable, basically. So that equals to -3p. Recall, if you increase the exponent by 1, so you get p, and we evaluate it from -2 to 4. So how we do this, we'll plug in 4 first, the upper limit first, so -3 times 4, minus, be very careful with negatives in this section, that's minus -3 times -2. So what do we get? We get -12, and here we have 3 negatives, so you'll have -12 minus 6. Equals to -18. Now you may think, well, how come the area under the curve and it can be a negative number? We're going to see that a little bit later. It's not really an area because sometimes you'll have the curve going below x-axis, so you'll get a length, which is the y of the function, negative essentially. That's what happens. But we'll see that a little bit later. But what about here? The next integral from -1 to 2 of 5t minus 3 dt. Again, you integrate as usual, so we'll get 5t squared over 2 minus 3t, and we evaluate it from -1 to 2. So usually here I would clean this up if possible, but I don't think we can do anything. Next, we can plug in 2 first, so usually I plug in, so 5 times 2 squared over 2 minus 3 times 2. So write this out, do not skip this step, because it really helps later. Then minus, then usually the next part I put in parentheses because you have the whole function that you're plugging into. Then I plug in -1. So 5 times -1 squared over 2 minus 3 times -1. And then the next step, again, I usually write them out and then I add them up. So 5 times 4 over 2, that's how come we got 10, minus 3 times 2, that's 6, minus, so 5 times -1 squared, that's positive 5 over 2. So that's how come we have minus 5 over 2. And then we have positive 3, but there was negative on the outside, so that distributes. So we have negative 3. So 10 minus 6 is 4, minus 3 is 1, and then 1 minus 5 over 2, that's 2 over 2 minus 5 over 2. So we'll get negative 3 over 2 as the final answer. Here is the same idea. If we compute from 0 to 2 zeros, usually the easier one to plug into. So here's what we have. 5x cubed over 3 minus 4x squared over 2 plus 2x, and that's evaluated from 0 to 2. The 4 over 2, you can actually reduce this. I don't think I did it, but you could have reduced it and make it 2x squared. I think I'd do that later. So you can plug in the 2 everywhere. And then I subtracted 0 because everywhere there is an x, so you're going to get 0. So the whole thing is 0. So really the lower limit, if the lower limit is 0, you basically can disregard it. If it's the upper one, you can probably disregard it too, but then you have to do minus the lower. So anyway, we plug in the 2, so we'll get 40 over 3 minus 8 plus 4. So that's 40 over 3 minus 4, and so you'll get 40 over 3 minus, I think, 12 over 3. So you get 28 over 3 is the answer. Okay. Same idea. Here we have an integral. This is the last example we'll do before we do area under the curve again. Sorry, let me get back. So let's focus. So if it's from 1 to 5, it's 6n to the negative 2 minus n to the negative 3. So with negative exponents, just as before, we'll get 6n to the negative 1 divided by negative 1 minus n to the negative 2 divided by negative 2, and that's evaluated from 1 to 5. Now here, I would clean this up before plugging in the 1 and the 5, because the cleaner the expression is, the easier it is to plug in. So what can we do? First of all those negatives in denominator, you can pull them out on the front and change the sign. And the negative exponent, in this case, we'll get rid of them because it's easier to plug in that way. So we'll get negative 6, it stays on the top, but n goes in denominator. Then we have negative, negative makes it a positive 1. Then we had positive 2 in denominator that's left, and then n, it should be n squared, really. Let me pause it and write it. Yeah, so let me add 2 in there. So that's 2n squared. So that becomes squared actually. So hopefully I do have it here. Yeah, I do have it. So minus 6, so we'll plug in the 5 first. Minus 6 over 5 plus 1 over 2 times 5 squared. And then minus, and then we'll plug in the 1. Negative 6 over 1 plus 1 over 2 times 1 squared, basically. So I get negative 6 over 5 plus 1 over 50. Again, I like to write this out. It really helps it out later. Plus 6 minus 1/2. A lot of times the answers in these would be in fractions in this section, and not until the next section we start writing decimals. So here I will work with fractions. The denominator happened to be 50, the common denominator. So basically bring it to common denominator. 5 to get to 50 multiplied by 10. That's how come I got negative 60. The 1 stays the same, so that's plus 1. Then 6 times 50. I got plus 300, and then 2 times 25, I got minus 25. So all that on the top, I got 216 over 50, which becomes 108 over 25, the reduced. So yeah, practice with fractions a little bit, maybe go a little bit slow in section 7.4 on the homework to practice. Okay, so here is the concept that I mentioned earlier. You get positive area if the curve is above x-axis because f of x is positive, and we get, so to speak, negative area when the y is negative or below x-axis. So that's how come some integrals give us a negative answer. And here are some more properties that would be really useful to us. Let me pull them all up. We have about 5 of them. Some of them may seem familiar to you. Notice if you have an integral from a to a, that's like having area at a point. You don't have area at a point, so that's just 0. If you have a constant, you can pull that out in the same exact way. If you have some difference, you can separate them and do them separately. Basically same idea. Here is a couple of useful ones. You can break up any interval from a to b as from a to c, then follow it up with c to b. Sometimes we have to break it up. That's especially with the area that we're going to do in the next section, area under the curve. Now c can be any number. It doesn't have to be between a and a b. But what can happen is that you may have a bigger number on the bottom versus the top, and that may seem a little strange because intervals are usually from smaller to bigger. So what we can do is take a look at property 5. This is an important one. If a to b, let's say a is bigger than b, it seems a little backwards. So what we can do is we can switch the sign, put a minus on the top, and make it from b to a, so you can always switch endpoints, but you have to switch the sign. That's kind of the price you pay for switching it. And what I wanted to do next, we're going to use these properties a little bit, but I also wanted to show you u substitution that was in section 7.2. It's very similar, but there's a couple of minor differences for the definite integrals. Okay, so let's take a look at maybe this one. Let's say if you wanted to compute integral from 4 to 6 of 2 over 2x minus 7 squared dx. So what we can do, as usual, we plug in u to be 2x minus 7, actually the inside function. Let's take the derivative of u as before, which will get du equals to, that's just 2, the derivative, and then times dx. Now here's a minor difference. You also have to plug in the endpoints into the u. So the lower one is x equals 4, plug it into the u, and we get 1. Then x equals 6, the upper limit gives us u equals 5. So we plug in for everything. So notice here's what we get. Integral from 1 to 5, the 2 times dx, recall that was du, divided by u squared. So that becomes u to the negative 2 du. Then as soon as we clean it up, we're ready to integrate, which becomes u to the negative 1 over negative 1. Notice integral sign is gone, and that's from 1 to 5, which you can clean this up. Divided by negative 1 is the same thing as multiplying, so you can pull it in the front, which is basically 1 over u, and we can plug in. This is another difference. You don't have to substitute for the u back, because we already substituted for the endpoints. We can just substitute the endpoints into the u and finish up with the integral. So you don't have to substitute u back the way we did in section 7.2 with indefinite integrals. So we can just plug in the 5. We'll get negative 1 over 5. And then remember, it would be minus negative 1, which will give us positive 1. So we'll get 4 over 5 as the answer. Okay? So those were the differences that I just explained. Here's another quick one, hopefully. Here is an integral from negative 1 to 0 of y times 2y squared minus 3 to the 5th power dy. As usual, the u is the inside function, 2y squared minus 3. The du is the derivative, so that's 4y times dy. Notice there is no 4 in the original integral, so we have to divide by 4. We'll get 1/4 du equals to y dy. And again, we'll plug in the endpoints. So if y is negative 1, we get u equals negative 1 also. And if y is 0, we get u equals negative 3. And here is where that situation happens. We have an integral from negative 1 to negative 3. Negative 3 is smaller than negative 1, but it's on the top. So it seems a little strange, and we're going to actually switch it to fix it. Then we have u to the 5th times the y dy. If you recall, that was 1/4 du. So you can pull 1/4 to the front. You can also, I switched the endpoints. That's how come we have the negative on the front. Remember, that was property 5. I like to switch the endpoints. Yes, you could have computed it without switching the endpoints, but pretty soon we're going to put the negative in front of the integral anyway with the area. So practice. If you ever have the switching with the u substitution and all of a sudden the upper limit is smaller than the lower one, you can always switch it and put negative on the front. So we'll have negative 1/4 times u to the 6 over 6, and that's evaluated from negative 3 to negative 1. We can multiply 4 and 6. It becomes 24 in denominator. And then I plugged in -1 first minus -3. So we'll get -1 over 24. And then we have -3 to the 6 is positive. So a couple of negatives makes it a positive also. So the answer is 728 over 24, which reduces to 91 over 3. There you go. Then a couple of compute area under the curve in this section. Also make sure leave up enough time for this section for the homework. Area under the curve. If you're given it, make sure to graph it. So if it's 2x minus 14, it's a line, so I just plugged in the 6. And I got -2, I believe, because it's 12 minus 14. -2 is the y. Then I plugged in the 10. I get 20 minus 14 is the 6. And I joined the whole line. So it should look like a straight line if you draw it correctly. Notice the piece from 6 to 7 is below x-axis. So that would have a negative area. And from 7 to 10 is above x-axis. Because we're trying to compute the area, in this case, it's important to get make any area positive, because if you don't switch the sign for any interval that's below x-axis, which is right here, by the way, right here, I'm just trying to cover it basically, you're going to get negative area, which is going to subtract from your total area, and you're going to get a smaller number than you originally would. So here's what you need to do. For anything below x-axis, separate that interval out, which notice how I broke up the area. So the first one from 6 to 7, notice how I put a negative on the front. Now in my math lab, in your homework, they use absolute values, which is another way to do this, I suppose. I usually put negative on the front to remind myself to switch the sign, because you'll get negative area, put negative on the front, you'll get positive. Or if you use absolute value, it's the same thing. So from 6 to 7, you'll have negative of this function, but from 7 to 10, you don't need to put negative because it's above x-axis, so it remains a positive. So it's really same integral, but you got to do this twice up to the negative sign. Notice how I did it from 6 to 7 with a negative on the front, and then I distributed the negative, so I got negative x squared plus 14x from 6 to 7, and then I get positive x squared minus 14x from 7 to 10. So hopefully you can follow my plugging in. First plug in the 7. Be careful with the negative on the front. That actually stays. Notice how I write everything out. I do write the numbers because they're easier to spot a mistake if you think you make a mistake. So I got 10 at the end. There would have been an easier way if you just would have computed the areas of a couple of triangles. I think I got 1/2 times 2 times 1. This was from 6 to 7. And then 1/2 times 3 times 6. That was the area from 7 to 10. So you could have done it with the triangles. But I wanted to show you with the integral too. So 9 minus x squared is the same way. I don't want to make this video too long. But when I graphed it, I noticed that f of x crosses x-axis at x equals 3. It is above x-axis from 0 to 3 and below x-axis from 3 to 6. This helps us to figure out what the intervals are, or our integrals. So integral from 0 to 3 stays positive. So that's 9 minus x squared. But then the integral from 3 to 6, I put a minus sign because it's below x-axis. Okay, so that's what determines if it's negative or not. So then I integrate it, so it's 9x minus x cubed over 3 from 0 to 3. But then I distribute the negative, so it becomes plus negative 9x plus x cubed over 3 from 3 to 6. Then I plug in, separate. So yes, it's a little bit longer that way, but so we plug in the 3 first. I got 9 times 3 minus 3 cubed over 3. Remember, 0 just gives us a 0, but I put it anyway. Then I just plugged in the 6. We had negative 9 times 6 plus 6 cubed over 3 minus, since we're plugging in the 3, this is how you know you're doing this correctly. Notice how there's 27 minus 9, and then there is again 27 minus 9 at the end. They should be the same sign. That's how you know that you're doing this right. So they should not subtract and cancel. There should not be too much cancellation in this case. So the answer would be 54 if you check all the signs carefully. And I think I did the same thing with e to the x minus 1. And the application was the same way, I believe. I'm just scrolling down because it's already 20-minute video. But I wanted to show you, I'm trying to write this the same way like I would write it out on a sheet of paper. Notice how I put u on the side, the du on the side, and so on. So hopefully you can follow it the same way. And again, 46.341 thousand at the end. I can multiply it by 1,000 and so on. So the idea is exactly the same. So yeah, this video is already long enough. It's 20 minutes, I believe. But that's the idea of definite integrals. So write them out. Do not rush through them. Make sure write it all the way to the end to simplify, and then add them up. And that's it for this section.